Yes, I actually planned for a 30-minute presentation, but I probably cut it down to 25. So when I practiced yesterday, we said there's a point at which we can stop. Okay. So my name is Ivar Thorson, and today I'll be presenting this robot on the right here. I've been working on it for 3 years. It's called JIMI. It's approximately 10 kilograms, stands about 1 meter tall. It's designed to move at about 1 meter per second. I've had it do squat jumps about 36 centimeters vertically. It's powered by 211 watt electric motors and has about 50 joules of elastic energy storage. And as a teaser video, there we go. Here's some preliminary results I've had of the jumping. I'm not entirely satisfied with these results yet. The Vicon system I'm using to measure orientation. It's a squat jump and I have to catch it because it doesn't have a landing routine yet. And in this presentation, I'm going to talk about as many of the details of JIMI as I can. I'm going to talk about the dynamics and how the mechanical and control dynamics were selected via simulation. Talk about the actuation system, the patented nonlinear series elastic actuators that I developed. I'll talk about the controller and how balance is achieved dynamically via passive space control of the Centroid. If we have time, I'll also talk about system estimation and how I do model-based system identification, the Asynchronous Dataflow-based concurrent software, and the carbon fiber structure that I constructed. So, part one. First, the dynamics of running. In this section, I'd like to proceed from animal-like characteristics of running, specifically a sinusoidal vertical ground reaction force, to a specification of actuation and control. So we'll start and ask, what best characterizes running? Is it having your feet off the ground, like Azimuth researchers claim? Is it having a single hump, vertical ground reaction force, or a double hump, like walking, in contrast to walking? Is it having this center of mass motion that is ballistic during flight, or is it having stance forces that resemble an elastic collision with potential energy and kinetic energy out of phase? Animals exhibit all four of the above characteristics, but for this presentation, the purposes of JIMI, I'm going to assume that it's the ground reaction force resembling an elastic collision that is key to running. So can we get a rough specification of what we're going to need to make the robot actually run? So if we assume that we have a ground reaction force that's half a sinusoid, and we want the sum of all the impulses to the center of mass equals 0 over a stride, so that it maintains a roughly constant height, we need the area under the sinusoid to be equal to the area, the impulse to gravity. So we have to equate these two. That's easily done with a little bit of analysis, and you work out the height of this ground reaction force. You work out the peak ground reaction force, and you can, depending on how long the stance phase is relative to the total stride, you can work out that if you have 90% of the time on the ground, there's just a little bit over 1.5 body weights. And for the duty cycle that I was working with JIMI, I need about 3 body weights of maximum ground reaction force. If we have a characteristic ground reaction force, we can also just integrate forward and work out the center of mass motion. So it'll be a parabolic arc during flight, and then sort of mix between a sinusoid and a parabola, I guess, during stance as it applies this sinusoidal vertical ground reaction force. We can also work out the power of the ground reaction force on the center of mass and get this very elastic mechanism, or very elastic profile, sorry. And we can work out the total change in energy. So roughly, for a 10 kilogram robot with 1/4 of a second stance and flight times, we need to have about 25 centimeters of total vertical motion, 20 joules absorbed and released per hop, and about a peak of 250 watts of mechanical power. So that gives us the total system power. What exactly do the joint torques look like? Well, if we assume we have a revolute jointed animal, runner, robot, whatever like this, and we have a ground reaction force going from the toe through the center of mass, I think it's reasonable to sort of cut and just look at one of these joints individually to get an idea of the characteristic type of torque. So I took this model here on the right, and I'm going to say this is a reasonable general pace approximation, ignoring inertia of the leg, to see what kind of torques we'll get and what kind of velocities we'll get at each joint in a jumping robot. If you do that, and you start the robot from various postures here, and it bends its legs down to these postures here, you can work out, as it creates a sinusoidal ground reaction force from these postures, you'll get torque angle relationships that are roughly quadratic to roughly linear. So you'll know that an elasticity somewhere between quadratic and linear will be perfect for a robot topic. Similarly, you can also work out the maximum angular velocity, or the angular velocity as a function of, the angular velocity and torque relationship as it creates a sinusoidal ground reaction force. So from this simple analysis, I was able to work out a roughly 120 Newton meters of torque, 10 radians per second velocity, and then the linearity is between quadratic and linear. So assuming a vertical ground reaction force gave us the motion, power, and energy of the center of mass, as well as the peak ground reaction force levels, and assuming some revolute joints gave us a very rough character of the type of joint nonlinearity, or the torques and the velocities that we'll see. So can we design an actuator that's custom, then will satisfy the above specifications? Yes. So from part 2, the nonlinear series elastic actuators that I developed. I'm going to talk about very quickly what is series elasticity, the optimal type of elasticity for running robots, and the hypocyclic mechanism that underlies both of these designs. So what is a series elastic actuator? It is the purposeful introduction of an elastic element between the motor transmission and the load. And the effect of a transmission is well known. It increases the torque in times, but it also increases the inertia of the rotor in squared times. This is well known. So the dynamic stiffness, if we were to push on the transmission, it would be n squared inertia of the motor times the frequency squared, which would be quite large at high frequency. If we insert a spring, the dynamic stiffness is much lower, the mechanical impedance is lower, essentially, and so we can have better force control, as we see in the next slide. There's improved impact resistance, we have a place to store energy. On the other hand, there's some bad effects. We have an extra degree of freedom, force bandwidth is reduced, and controllers can waste work compressing and decompressing the spring to create force. So Williams did a simple analysis of what's the effect of a spring. So assuming a model like this, we'll just let the damping terms go to 0 for right now. The torque on the rotor as a function of the joint torque and motion, the only term that's unique to series elastic actuator is this one. And there's a resonance frequency shown here. And for below 2 times this resonance frequency, the effect of the spring, this red term, is exactly opposite the joint torque term. So for bandwidths below the 2 times the natural frequency here, or I guess the square root of 2 times the natural frequency, a spring will improve your force control always. But what about nonlinearities? I'm trying to create a ground reaction force that's sinusoidal, and I have a nonlinearity in the joint. And if I use a linear elasticity, actually, when I do a simulation, I get rotor motion that's not very sinusoidal. The previous analysis is complicated by these high frequency little wiggles. And the solution that I'm using is to mechanically use a nonlinear elasticity to create a rotor motion that is almost perfectly sinusoidal, which means that the natural oscillation between the rotor and the elasticity will work in my benefit. So what exact mechanism do I use to create this nonlinear elasticity? I'm using a curve called the hypocycloid. Hypocycloid is when a small circle rolls inside a larger circle without slipping, and a point on the inner circle traces out a hypocycloid curve with a number of cusps equal to the ratio between the outer and inner circle. So 4, 3, and 2. If you draw, if the ratio between the inner and the outer is 2 to 1, you draw a perfectly straight line. And this perfectly straight line, now shown here in vertical, as this rotates around, we can use to stretch a spring. And if you stretch a spring in this manner, depending on the pretension of the spring, you can create a family of angle to torque relationship, essentially stiffnesses, that are from quadratic approximately to approximately linear. These are different pretension values shown here. So it's a very ideal family of curves for jumping and running robots that have revolute joints. The first prototype looks like this. It's quite large. Thank you, John Luca, for helping me with the design of this. This is what it looks like internally from the patent. This is the long output arm, and shows that there's a spring internal, a large tension spring. And now I'm going to show a very short video showing that even without any load cells or sensors, just measuring the deflection of the spring, you can perform gravity compensation that just needs finger pressure. It's also still very robust to fast impacts. It can produce quite a bit of torque. And has a natural resonant frequency that can be very useful for, it can be exploited for jumping robots. So, as a quick aside, I noticed while I was doing these experiments that this actuator is extremely back-drivable and can in fact regenerate mechanical energy into electrical energy. So I did a quick experiment. I attached 2 kilogram mass to the end. I used a battery and a brushless DC motor controller set to provide very low voltage, and I swung the pendulum down from a vertical orientation to the 180-degree position. And when I did that, I recovered 65% of the energy. There's possible total of 21 joules of energy released by that motion, gravitational energy, and almost 14 joules were recovered with a peak generated power of a little less than 45 watts. So the results from the first actuator, it had good impedance, good impact resistance, back drivability, it could regenerate energy, it could store a lot of energy in the spring if the rotor was locked, but it was much too heavy, it was too big, there was too much friction, and the electrical limits were preventing me from reaching the full mechanical limits. So I needed to do a second revision. And this is the second revision of the hypo-SEA actuator. It's considerably smaller. It weighs about 2.9 kilograms, and the internals have also been simplified. So, to summarize, it's lighter, it's smaller, has approximately the same torque, but it stores a little less energy. And in a very brief schematic diagram, this is how the torque control of the actuator is accomplished. This shows the sort of output load. This would be the mechanical domain, showing a second-order integrator and elasticity. The electrical domain, I only have voltage control of the system, so I have to have a first-order compensator in the controller that creates the desired current, and I essentially do PD control of the deflection of the spring to create to do the torque control. So in summary, the hypercyclic mechanism makes the best use of limited rotor torque by closely matching the expected joint torques of running. It's light enough to use in a robot, and I need bigger motor drivers to really test these things to maximum. So now let's look at the balancing controller. I just showed you the joint torque controller, so now we're going to go up in this section, talk very quickly about inverse dynamics, how the center of mass pass-phase stabilizes the robot, and the 3 decomposed controllers that actually perform the control in the task phase. So I think most people are familiar with the conservative equations of motion over here with inertia, Coriolis, and gravitational terms. This term represents the effect of the joint torques, and this term is the foot Jacobian along with the ground reaction force. So if we want to then go from a set of desired foot forces or desired foot accelerations during stance and flight respectively, we can use standard, normal textbook inverse dynamics to work out what the joint torques would be in such a case. So during stance, the controller essentially tries to control the foot ground reaction forces. There's 2 degrees of freedom, and there's only 2 ground reaction forces, so it's a simple, unique solution. During flight, there's one constraint where you try to create the motion at the foot that you desire relative to the center of mass. And once we have control over the forces or acceleration of the foot, we can create a centroidal task space where we just essentially reparameterize the motion of the foot in terms of the length, virtual leg length, measured from the center of mass to the foot toe, or the torque, about the center of mass. So it's just a polar coordinates essentially. So then control becomes very simple. It can be accomplished with 3 controllers, which are basically PD controllers. The vertical reaction force is determined by having a rising virtual reference point and a virtual spring on the center of mass during stance. And this adds a constant amount of energy and creates a sinusoidal vertical ground reaction force. The horizontal ground reaction force is simply a PD controller over here that works on the angle of the centroid. It's sort of a virtual angle. There's no real physical angle there, but it's a combination of the leg orientations. And the angular momentum of the center of mass. And then finally during flight, you just need to contract the leg, swing it forward, and bring it down again. So a little trajectory tracking and some sinusoids is all you need. You really can't see that very well, but these are the simulation results that I did about 2 years ago before I began actually designing. And I studied power and motion and forces and everything I could do in order to try to make everything consistent with each other. So this was an old simulation. You can see the robot looked a bit different, and it hopped a little bit different also. But the point was that I studied the dynamics of the controller, the actuators, and the rigid body dynamics in simulation before I began. And that I found that three simple rules were enough to stabilize the robots using the centroidal task space. And that rotor work could be minimized by matching the dynamics of the controller and the mechanical system. So, in 15 minutes, can we now estimate the state and model parameters for all this model-based control? It's hard to actually get model parameters accurate enough to use. So, I'm going to talk very quickly about how I used model-based least squares regression and power constraints. We're all familiar with if we have a system like this, and we perhaps can measure the position, but we don't measure the velocity directly. And we might know the one parameter very well, but we might not know the other parameters very well. How exactly can we numerically work out what the optimal values would be? So assuming we have a real value shown in red, you can't really see it here, you can see it down here. We can take a finite difference, just taking the difference in position with this shows the noise created by discretization. We could use an averaging or low-pass filter, perhaps a central low-pass filter if we're looking for smoothing data from the past. And that works a little better. We could use polynomial regression, like a Savinsky-Goulet 9th order filter, one's causal. Or we could use model-based control. And I'm of the opinion if models can improve control, models can improve estimation. And so I used a 4th order model-based smoothing, or I guess, smoother, which is tracking very closely and very smoothly the true velocity of this simulated system. So how exactly do I do that? Well, if we have a linear system described by ordinary differential equations like so, this is familiar to many control theorists, and we have some process noise, delta, and some measurement noise, epsilon, it's pretty hard to beat a common filter or one of its variants, even if these terms are slightly nonlinear. It's pretty hard to beat that. But if we're going to smooth past values, if we don't have to be causal, you can use central differences and get a better approximation of what the values would actually be. So for JIMI, I came up with I don't really know what to call it, but it's a 4th order central difference weighted least squares approach. So to understand that, if we look at what a common filter is, there are 3 terms here, C, which are the measurements. It's the measurement term over here. And we have 2 equations that are relating the previous state to the next state. So if we were to look at it as an incidence matrix, we would have essentially a bidiagonal previous state, this state, and connecting all of the states there, which we could then work out what the rates of change are. So a 4th order system would be central 4th order discrete differences matrix would look something like this. You take a bunch of your data there, and you've constrained it not now just to the state immediately preceding it, but to states a little bit before and after, and you get a much more accurate estimation of the rate of change of the state. And when you actually have to solve it, you can solve it one constraint at a time, or you can collect a bunch of states, and it's a very flexible technique for smoothing past data. Once you have your smooth past data, you can then begin to estimate, well, what are the true mechanical parameters for A and B now that we have a nice x dot and x and u. So my observation is that if the model is good, excluding external disturbances, the power in and out of the system should be 0. I mean, we should have a good power budget. There shouldn't be energy disappearing from the system. So I have been using a least squares parameter estimation technique where I minimize the power error, using energy as a sort of lingua franca, a way of comparing different physical parameters. I use a Hamiltonian formulation, incidentally. And if you were to expand the terms of these A and B matrices into something like this is a typical traditional least squares approach. You put all your parameters in a big vector. You compute, sometimes this is nonlinear, but you compute a function, the power error, and make it a linear function of the parameters, and then do weighted least squares, depending on how certain you are of the model measurements. So in real time, I use a Kalman filter as a summary here. I use a Kalman filter. Smoothing can be done with a higher order model-based filter. It works quite well. And from that smooth data, we can iteratively improve our estimate of the model, such that the power is conserved. But I haven't actually done this yet for the full JIMI model. I've only done it for the ACtuators. So it's been 20 minutes. If I may continue for 5 more minutes, I can do one more section. The data flow system that I use for this programming style. I'm using a language called Clojure, which was invented by Rich Hickey about 3-4 years ago. And I had a lot of motivation to do it because I was really irritated, and I'm not going to bore you with all those. But the core part of Rich Hickey's idea is to follow the idea of pure functions and immutable data. So instead of using a variable where things change in the background, it's you use a name and you use values that are associated with that name at a particular time. So A becomes sort of a pointer to data instead of actually containing the data itself. You then create a linked list or a tree or whatever the data structure requires, where you relate past values to the next value using a pure function that only takes as the inputs the mathematical values. So I guess it's a return to mathematics. And if you were to read the value of A, during this point of time, it would be A equals 1. It would instantaneously change. It's an atomic change. And then during this period of time, you read A equals 3. And an advantage of this kind of this approach to state and change is that names only point to one thing at a time. Because this underlying data never changes, you can use it by as many threads as you want. You don't have to copy old data if you want to use it from another thread. You can just safely reuse it because it will never change. It will just be garbage collected after there are no more references to it. And this allows a great deal of concurrency. My minor extension to that framework was to tightly couple the function that computes the data to couple the two together. So couple the update function with the data. So whenever an input A would change, this X would immediately be notified of that, and the data would keep itself updated using a thread pool. So these little bits of work would be pushed onto the thread pool, and they would keep themselves updated. So you can make trees, and this allows for great concurrency because all of these computations can be done on different processors. So the data keeps itself updated. It's always safe to read. You can isolate bugs to just one particular computation that you're doing wrong. And you can add new flows at any time because the Clojure is a dynamic language. So there are, of course, some complexities to that I will skip over. But
It's kind of keen to draw it to a conclusion, I think.
yes, okay. So I'll show a very short video of this is the system working. Here's the Vicon data in the background. This is the reconstructed orientation of the robot based on the markers. And this was an oscilloscope that I also wrote to measure the virtual signals. I can't really see it very well, but all of the signals in the system. So, here's the oscilloscope. Here are some of the motor controller GUIs that I wrote to actually change. For example, this is the Kalman filter, so you can change all the parameters as you want. And this is the motor board, and you can change the parameters of the motor board dynamically. It's all very fun. So in summary, the software architecture, the data flow allows for remarkable concurrency. It's very simple. Clojure is a very nice language. The latency in these systems was quite good, about 100 microseconds, and it would improve if it was optimized. But because this is running on a non-real-time JVM, Java Virtual Machine, a real-time garbage collector would help improve performance to get rid of some erratic 5 millisecond pauses and to provide true things. And I'm out of time, I guess. The optional thing I was going to talk about was how I made the carbon fiber points, but I'll go to the conclusion unless. No? Okay. Go down. Second, 90 seconds. So there's a couple more photos of the robot. This shows the back. There's some air holes. Only 2 wires come in. It's got some rubber stops in different places to prevent it from getting injured. There's a lot of space in the torso for a controller and a battery, if I can ever get the balance perfectly well. It has a rubber boot on it to protect it when it falls, and there's very little protecting it when it falls, so I'm quite worried it's going to damage itself as it jumps higher and higher. And the conclusion is the basic concept seems to work. I'm having difficulty with irregular Vicon latency at the present. I'm going to continue working on this for a few months. The joint torques are not optimal as they were in simulation. I'm having great success with the asynchronous data flow system. However, the really simple ground reaction force control I presented to you has a singularity when the leg is straight. The carbon fiber pieces are very lightweight, but it's kind of hard to disassemble in the way I designed it. The force control works well, and if I can figure out a way to get more power to them, then we can try to break them better. And it also regenerates energy. So some future directions that can be pursued from here is to see how high it can really for me to run and jump. To maybe release the Dataflow software. Can it be rebuilt a little better, perhaps, for a motor driver to be used to improve performance? What trajectories might maximize energy recovery? There's some interesting things to do. If anyone's interested in using JIMI or the test high-frequency version 1 actuator, please come talk to me. I'd like to thank Gianluca Pani and Phil Hudson for their help with mechanical and electrical respectively. Nikos and Darwin, and the whole Heki group for tolerating me being in their space for the last 3 months. Thank you very much.
Out of curiosity, is you're planning to use this as a like a modular line for more complicated problems, or
No.
hard or just hard?
My goal was to study a nonlinear system that was simple enough that I could study it, but not so simple as to be trivial. And there's a lot of nonlinearities in a jumping robot that bounces on one foot. It would be interesting to take 2 of these, bolt them together, and make a biped robot, but I have no plans to do that at the moment. I want to make this work as well as I can in the next 4 months.
Sorry for asking.
You can get to slide by slide. Get to slide 16.
If I can go to slide 60?
16.
16. Okay.
Part of my road down for getting to 69 slides.
Yes! Okay, slide 16. 16. Okay. If you'd like, I have a printed copy here that maybe you can reference better.
Having some proper understanding how you matching this to the physical system.
So this shows a 3-cusp hypocycloid being drawn by the point P. And the next slide, I went over this very quickly, but this would be the point P. So as this ball, or as this rolls around the inside of this, imagine that this is the point being driven. So from the center, as you bring it in either direction, you're deflecting this, you're stretching this spring. And that spring deflection is coupled to the system via a differential. So there's this motion would be driven by the difference in the output link and the transmission. And mechanically, it's kind of hard to see when I show
So the biggest issue there would be the selection of the spring.
the selection of the spring should. What I did was try to fit these curves and the pretension, because you can pretension this if I start pulling on this spring by increasing the mass, it becomes more linear. So if you have no pretension, you have this almost zero stiffness, incremental stiffness around the equilibrium point, which is cool for some things because it can allow very, very low impedances, but it's more difficult to control the system because it's more nonlinear. So your feedback has to be gained. Yes, I have to model a lot of things to control it properly.
Yeah, two questions. One question is that can you give some commands about the work done by Mark River? So because he also Mark River
For controlling?
for the jumping robot, and because he also used something like thrust,
Yes.
and determine how much time,
Yes.
and which is determined by energy you want to inject. So it looks very similar.
It is indeed very similar. I started actually with Mark Rayberg's 3-part decomposed controller for running. But there are a few small differences in this. First, I'm not using a telescoping leg, so that was recreated virtually using the vertical ground reaction force. I also do not kick the leg forward. I swing it more gradually. He uses a Ph.D. controller that kicks the leg forward, so that controller is also a little different. And then the angular momentum of the robot, because I cannot assume that the mass of the body is much, much greater than the mass of the leg, I cannot use his controller very well. It would destabilize the robot. I couldn't find a way of making it balance. So the angular momentum controller that I showed briefly considers the effect of the angular momentum of the leg and works out sort of a compromise between moving the leg like that to lean the body forward, and kind of goes like, I don't know, it's hard to describe, but it's quite simple mathematically.
So I mean that how fast the robot can hop determines also by the swing motion, right?
In simulation, I couldn't get it to hop faster than about 1.5 meters per second, unless the powers of the actuator started getting quite high, like 500 watts or something like that. I think that's your question.
The second question is that do you have some algorithm for foot landing control? So Mark River proposed something like neutral point.
Yes, I'm using exactly the neutral point algorithm. Yes, that works beautifully. You don't need to change that.
So you use the exact same.
Can I just follow up on George's question, which was, well, what I'm interested in, I'm wondering whether this sort of single-leg hopping robot is likely to be a commercial viability, or whether you're just using it, as you said, as a model in order to develop other things. Because, I mean, in nature, there's no single-leg hopping animals, but there are two-legged with a tail hopping animals.
Kangaroos.
That seem to use a lot of these tricks, like, you know, the tail is a spring, and it recovers a lot of energy. But then you don't have all the stability problems that you seem to be running into. So I'm just wondering whether you're creating more problems for yourself, restricting yourself to one leg, and giving yourself a tail to stabilize.
I did make life difficult for me by not having a large inertial ballast, I guess you would say, a tail or something to help balance the robot. That would help immensely, as would adding bars to increase the inertia of the torso, would make it much easier to balance. I think that a third degree of freedom on a leg like this would help dramatically, because there's two degrees of actuation, one at the knee and one at the hip, and there are only that only gives me two things I can control, the vertical ground reaction force and the horizontal ground reaction force. But there should be a third degree of freedom to regulate the internal angular momentum of the entire system. And if it could control its posture without having to throw away its ability to control the posture while it's controlling the forces on the foot, that would be very useful and would make it much more stable. So I think there's a reason that we have 1, 2, 3 joints in our feet when we're running, when we run on our toes, rather than running on our heels as much. It's much easier to stabilize with a third degree of freedom. But I learned this, 18 months into the project, rather than at the beginning.
What was the main reason we just settled for common filter?
Because the fourth order smoothing system that I developed requires future data. So if I want to estimate where I am now, I need 2 or 3 values from the past and 2 or 3 values from the future. And that works better than a causal filter, where you only look at values in the past, because those typically under or overestimate the true value of the system. And if I do that for parameter estimation, it doesn't seem to work as well as, I mean, it's cheating, right? You wait longer, the longer you wait, the more data you see, the better you can estimate. But for up to the instant control, I couldn't be picked out. It's optimal for a particular class of problems.